Today we study ESA15H, Euler's formula e to the I theta. The exponential function is defined by this relationship of the differential of the exponential. It becomes the same factor multiplied by the differential of x. The condition for this function is exponential to the 0 is always 1. Restrict ourselves to the region where the positive x is much smaller than 1. And at the end of the day, we will find that this can be, the expansion is true for all finite values of x. First of all, because of the fact the exponential function f of x equals e to the x has a condition that f of 0 equals 1. We can expand the power series in x. That we have a coefficient for each power of x. First of all, because we have this constraint, we can substitute 0 for x to find everything vanishes except for the C0, 0 to the 0, that is 1. So C0 multiplied by 1, that is a C0. And our condition is that C0 equals 1. We can make use of this fact. The differential of exponential divided by differential of x is identical to e to the x. We apply the derivative operator d over dx one more time. Then we have the dx squared, the exponential x, that is a dx dx, that is the exponential x. So whatever times we multiply this apply this operator, we end up with the same function, exponential x. So for any k, the application of differential operator to the exponential function results in the same function. Because of this, we can apply this operator for the right-hand side, this power series expansion of the exponential x in powers of x. We know how to find the derivative of the polynomial. We apply this derivative operator by k times. The power of each term decreases by k. And we have additional factor that comes from the power j and next derivative j minus 2 and so on. So we have this additional factor. By the way, if I substitute the 0 after taking the derivative by k times, we have the only single term survive. The lower power, the powers of x lower than k vanishes. For example, if I take the derivative of 1 with respect to x, it becomes a 0, something like that. That is x to the 0th power. If I have a power 0, only a single derivative will result in 0. If I take the derivative twice, the x to the 0 and x to the first power, both of them vanishes, something like that. In addition, because we have substituted the value at x equals to 0, any powers will disappear. So the only contribution after substituting 0 for x is the constant term that does not have x after taking the derivative, kth derivative with respect to x. As a result, if I substitute j equals k, it becomes 0, and it becomes a k. And we have k, k minus 1, k minus 2, and so on to arrive at 1. That is identical to k factorial. So ck multiplied by k factorial is the kth derivative of the x to the j term, whose coefficient is cj. As a result, if I sum everything over j from 0 to infinity, the only contribution survives like that. We know this one. We know this. What we have found is the left-hand side, and we know what the right-hand side is. That is this. As a result, if I compare the both sides, what we find is ck is 1 over k factorial. As a result, the expansion, power series expansion of the exponential function is like this: x to the k over k factorial. We consider the definition of Euler's number E. This one is another definition of the Euler's number. Let's see. Exponential x can be computed by taking the power x. For simplicity, we just consider positive x, and it is smaller than 1. But, however, we can extend this one, extend the region to any arbitrary value of a real number x. In fact, it can also be extended to any complex number. But for the time being, we just consider the simplest case. After taking the power x, what we find is this. We can rewrite 1 over n by multiplying x over x, that is identical to 1. After that, we find this power nx, because we have chosen x to be a positive number, and we take the limit as n goes to infinity, positive infinity. Why don't we replace this one with another large number that approaches infinity, that grows of infinity? Okay, so we have redefined n times x by n. Now we arrive at the same expression, except that we have a x over n instead of 1 over n. Now we can apply what we learned is the Newton's binomial theorem, for the generalized binomial theorem. But in case we have integral power, then we can apply the binomial theorem directly. So a plus b to the nth power, this one can be expressed as this binomial coefficient and a to the k and b to the n minus k. Now we have a equals 1 and b equals x over n, x over n. Now we can find this binomial coefficient can be expressed in like this. By the way, this factor must vanish. This one is wrong. This one is wrong. Because we have n minus 1, and so on to arrive at n minus k plus 1. n minus k to arrive at 1. And in the denominator, n minus k factorial is identical to this factor, so they cancel. So after the cancellation, what we have is this factor removing n minus k factorial out of n factorial. So therefore, this one should be deleted. Now, why don't we absorb this n to the k into the denominator factors? The numerator factors has from n to n minus k plus 1. They are k factors. So we have a k to the power of n. So we distribute k factors of n into each factors. Then we have the n over n is 1. N minus 1 over n is 1 minus 1 over n, and so on, to arrive at 1 minus k minus 1 over n. In the limit, as n goes to infinity, these contribution is negligibly small, and that does not contribute to the sum. And that is identical to what we have found by solving the constraint equation for the power series expansion of the exponential function. As a result, we have two kinds of expression. E equals a limit as n goes to infinity, 1 plus 1 over n to the nth power, and exponential x equals the limit as n goes to infinity, 1 plus x over n to the nth power, and it is identical to the sum of k as k runs from 0 to infinity, x to the kth power divided by k factorial. Everything, this one is identical to this. We are interested in extending the additional contribution that has a larger power than 1 over n. That means 1 over n squared, 1 over n cubed. Any kind of powers with some finite number is included. You can do it yourself, but anyway, this factor again must be deleted. This factor must be deleted. And in this, we apply the same approach to find that the additional contribution vanishes in case as long as this power is greater than 1. As a result, additional power contribution in the parentheses do not contribute at all. So they do not contribute to the final result, and the result is identical to the exponential of x. Whatever power, as long as its power is greater than 1, it does not contribute to the final result, and the final result is identical to the exponential function. Next, we extend this one by substituting I theta for the x in the expression for the exponential function. The power series expansion gives a very simple expression. We divide this into two pieces with the even powers. Now we have even powers, and in the denominator, k is replaced with the 2k and odd powers. We know I squared equals minus 1. So I cubed is minus 1 times I, that is minus I, something like that. As a result, if I take the kth power of this, we have I to the 2k is minus 1th kth power. And if I multiply I to both sides, we have odd powers of I, and the right-hand side is a minus 1 to the k multiplied by I. As a result, I can replace this I 2k, theta 2k, and I 2k plus 1, theta 2k plus 1. Why don't we replace this one with this? We find these even powers are all real numbers, and they are replaced with this. Odd powers are all pure imaginary numbers because we have a single I as a vector. Finally, we collect all of them, that we can sum these two. We have made use of identities. The identity shows this is cosine and this is sine. A similar method that we have made use of to find the power series expansion for the exponential function can be used to find the power series expansion of cosine and sine. Okay, cosine is an even function, and it consists of even powers of theta. Sine is an odd function. It consists of odd powers of theta. And it is trivial to see sine theta goes to 0 as theta goes to 0 from this expression. And you can take the derivative of sine or cosine to find the derivative of cosine is minus sine, and derivative of sine is a cosine. So this is called the Bernoulli's definition. Bernoulli's definition of exponential e to the x equals 1 to the x over n, and limit as n goes to infinity. This one is quite useful to find out the law of exponent. For simplicity, h vector, we use the same power, n. In that case, I can pull this outside and expand the factors. It will give 1 over n term contribution and 1 over n squared contribution. We recall that higher order contribution does not contribute to the final result of this limit. Only constant plus 1 over n style contribute to the exponential function. As a result, we can neglect 1 over n squared contribution inside in the parentheses, and we arrive at the point that exponential z multiplied exponential w is identical to exponential z plus w. And this z and w do not have to be real numbers. They are all allowed to be complex. We recall that the rotation matrix on the two-dimensional plane is cosine sine minus sine cosine. And in the case, if we keep the axis of rotation to be invariant, they are commutative, and we can repeat the same rotation by n times. Then we arrive at the same rotation matrix. That means that we divide theta into two pieces and repeat this small amount by 2 times. Then we have the same rotation. And this can be increased to 2 to 3 and 4 and arbitrary integral number, integer n. So R of theta over n repeated rotation by n times is identical to the rotation matrix for the finite angle theta. And we can increase this n arbitrarily large. Whatever number we may apply, the result is identical to the rotation matrix finite for the finite angle. So why don't we look into the expression for R theta over n as n goes to infinity. We remember cosine approaches 1, and it consists of even powers of theta. So leading contribution of cosine theta as the theta goes to 0, so it should be theta over n instead of theta. It should be sine theta over n. It becomes 1 minus theta squared, 2 factorial in the denominator, n squared, and so on. And sine theta, this leading contribution, and the cubic term. In a similar manner, we can express the remaining 2 elements like that. We collect the theta-independent term, that is a theta-independent term, that is identity matrix, and the linear term, that is theta over n. We have negative sign, positive sign. So we define a matrix whose off-diagonal elements are -1 and 1, and whose diagonal elements are all vanishing, so it's a matrix. In a similar manner, we can separate the leading contribution next to the leading contribution in this form. We recall that this one is, we have additional power of this. We remember that 1 plus a over n, a b over n squared, and so on, nth power. If they are finite, all of the contribution vanish exactly, and only the 1 plus the leading power, that is 1 over n, contribution survives to contribute to the exponential a. As a result, we find this one is exponential theta a, where a is a matrix. We do not know how to compute the exponential of a matrix. However, we know how to compute this by making use of power series expansion. Power series expansion is all known. All right. By the way, we can make use of this matrix A. Why don't we square this? The final result is identical to the identity, except that we have negative sign on it. Just like what we have done with the pure imaginary number I, if I square this, I have negative sign. Something like that. Its matrix has a very special property that if I square this matrix, it is identical to the identity except that we have negative sign on it. So if I repeat and multiply this by even powers, it is identical to identity matrix except that we have -1 to the kth power. If I multiply this matrix A by odd powers, odd times, then we have additional A and we have additional factor -1 to the k. Why don't we substitute these results into here after separating the series into 2 parts, even part and odd part? Substituting this one for the a to k, substituting this one for the a to k plus 1, what we find is some matrix, the identity and the original matrix A, and except that additional factors are identical to what we have found with cosine and sine. Finally, this one is identity matrix multiplied by cosine. This is a matrix A, 0, 0, and 0, 0 sine theta. And we need to sum them all. The result is cosine, cosine in the diagonal component, minus sine and sine for the off-diagonal component. It is identical to what we have expected, the finite rotation matrix for the two-dimensional plane with a finite angle theta. Okay, it's very interesting, and we call this matrix A to be the generator of the rotation. That's it for today. Thank you.